Hi students, my name is KVR, chemistry lecturer in Sri Chaitanya College, Dr. B.S. Rao Nagar campus, Gosala zone. I hope you all are doing good. Today I am going to explain you about one of the most important topic, that is molecular orbital theory in chemical bonding lesson. Every year from chemical bonding topic 3 to 4 bits will come in our Neet examinations. If you observe previous papers also, minimum 3, maximum 4 or 5 bits will come. Okay. Molecular orbital theory. It was proposed by Hund and Mulliken. The main purpose of this theory is to explain the bond orders and magnetic behavior of diatomic molecules. Okay, diatomic molecules as well as ions. In general, the electrons in an atom are present in atomic orbitals. You know atomic orbitals clearly, that is atomic orbitals are SPDF. What are atomic orbitals? Atomic orbitals are SPDF, like that. Electrons in an atom are present in atomic orbitals, but in a molecule, electrons are present in molecular orbitals. In a molecule, electrons are present in molecular orbitals. Molecular orbitals are formed by the linear combination of atomic orbitals having a proper symmetry and nearly same energy. That method is called LCAO method. LCAO method. LCAO method is nothing but a linear combination of atomic orbitals. Molecular orbitals are formed by this method. If psi is a wave function, it represents atomic orbital. Then let us consider psi A and psi B are the two atomic orbitals. When these two atomic orbitals combine linearly, they give two molecular orbitals. Here it is one atomic orbital of one atom, it is atomic orbital of another atom. When these orbitals combine linearly, they form two molecular orbitals. One molecular orbital is called bonding molecular orbitals. Another one is called anti-bonding molecular orbital. This type of combination of atomic orbitals is having proper symmetry and nearly same energy is called LCAO method. Molecular orbitals are formed by this method. When two atomic orbitals combine, they give two molecular orbitals. That means number of atomic orbitals combined is equal to number of molecular orbitals formed. Okay. Molecular orbitals are two types. One is called bonding molecular orbital. It is formed by the addition of wave functions of atomic orbitals. Another one is anti-bonding molecular orbital, that is formed by the subtraction of wave functions of atomic orbitals. Addition of wave functions is nothing but constructive interference. Removal of wave functions of atomic orbitals is called destructive interference. Okay. Here, number of atomic orbitals combined is equal to number of molecular orbitals formed. Number of atomic orbitals combined is equal to number of molecular orbitals formed. For example, if Avogadro number of atomic orbitals are combined, if Avogadro number, that means Na, of atomic orbitals are combined, then how many bonding orbitals are formed? Half bonding molecular orbitals, half anti-bonding molecular orbitals are formed. Okay, if Avogadro number of atomic orbitals are combined, number of bonding orbitals formed equal to half of the Avogadro number, remaining half anti-bonding molecular orbitals. Okay. If you observe the order of energy of molecular orbitals, energy order is bonding molecular orbital has lowest energy compared with atomic orbital. If you observe the LCAO diagram, in that diagram, bonding orbital has lowest energy compared with atomic orbital. Atomic orbital has lowest energy compared with the anti-bonding molecular orbital. It is the order of energies of molecular orbitals. Okay, these simple points are also important. Molecular orbitals are mainly two types. They are bonding and anti-bonding. Bonding orbitals are formed by constructive interference. Anti-bonding orbitals are formed by destructive interference. Number of atomic orbitals combined always equal to number of molecular orbitals formed. When two atomic orbitals combine, we will get two molecular orbitals. One is bonding, another one is anti-bonding. If an Avogadro number of atomic orbitals are combined, we will get half of the half bonding, another half anti-bonding. Here n by 2 are bonding molecular orbitals and remaining are anti-bonding molecular orbitals. Okay. Electrons present in bonding molecular orbital stabilizes the molecule, while electrons present in anti-bonding orbitals destabilizes the molecule. What is the major difference between atomic orbital and molecular orbital? If you observe these shapes, atomic orbital is monocentric, while molecular orbital is polycentric, but that means it is influenced by more than one nuclei. Atomic orbital is influenced by only one nuclei. Okay, these all are theoretical points. Read NCERT book carefully, line by line. These are all also important before going to bond order calculation. And here representation. Molecular orbitals are represented by sigma, pi, delta, like that. You know already atomic orbitals are represented by sp, df. When sp, df orbitals combine linearly, we will get molecular orbitals. They are represented like this: sigma, pi and delta. In these orbitals, bonding orbitals are represented by bonding molecular orbitals are represented by using like sigma, pi, delta. Anti-bonding molecular orbitals are represented by using star sigma, star pi, star delta, like that. Okay. Based on the above important postulates, now I am going to write the energy level order of the molecular orbitals, filling of electrons into various molecular orbitals. While filling electrons into molecular orbitals, orbital with lowest energy filled first. That means bonding orbital is filled first, followed by the anti-bonding orbital. Okay. Here, if z-axis is considered as internuclear axis, then according to molecular orbital theory, pz overlapping always leads to sigma bond. pz head to head overlap always leads to sigma bond. Remaining px py sidewise overlapping leads to formation of pi bond. If z axis is considered as internuclear axis, pz orbital form sigma, remaining to form pi bond. Sigma orbitals and pi orbitals. Then molecular orbital energy level filling order up to 14 electrons or atomic number Z value less than or equal to 7 is up to 14 electrons means up to N2 molecule, up to N2 molecule, nitrogen molecule. Because this configuration is important. While writing this configuration, first write bonding orbital, next write anti-bonding orbital. Sigma s 1s star sigma 1s. Sigma 2s star sigma 2s. Bonding, anti-bonding. Bonding orbital has lowest energy compared with anti-bonding. Sigma 2s has lowest energy compared with sigma star 2s. After that, electron enter into pi orbital, pi molecular orbital, that is pi 2px and pi 2py. If z axis is considered as internuclear axis, pz orbital form sigma, px and py form pi orbitals. Okay. First right bonding, sigma 2pz. These three are bonding orbitals. After that, write same orbitals with star. These are anti-bonding orbitals. Okay, it is the molecular orbital energy level filling order up to 14 electrons. Up to 14 electrons, after sigma star 2s, electron enter into pi orbital. Okay, it is the important point. It is based on spectroscopic studies. Based on spectroscopic studies, molecular orbital energy level order is like this. While writing this order, follow first bonding orbital, next anti-bonding orbital, because bonding orbital has lowest energy. That's why it is filled first, followed by anti-bonding orbital. While filling the electrons into above orbitals, all three rules like Pauli's principle, Hund's rule and Aufbau principle are used. In degenerate orbitals, Hund's rule is applied while filling electrons into degenerate orbitals. Here pi orbitals are degenerate, that means they have same energy. So writing 14 electrons into above orbitals, each orbital 2 electrons up to sigma star 2s2, pi 2px1 9th electron and 10th electron, because these two are degenerate orbitals. Each degenerate orbital filled with 1 electron, then only pairing takes place. That's why 11th electron paired with 9th, 12th electron paired with next electron, 12th, 13 and 14. Remaining all orbitals are vacant. Remaining all orbitals are vacant. Okay. Here up to 14 electrons are there. Up to 14 electrons, it is the configuration. If Z value greater than 7, then molecular orbital energy level order. That means heavier elements like oxygen, O2, F2, while filling electrons into O2 and F2, filling order is like this. First 4 orbitals remain same, sigma 1s, star sigma 1s, sigma 2s, star sigma 2s. Okay. Here 9th electron will enter into sigma orbital, that is sigma 2pz. After sigma 2pz, write pi orbitals, pi 2px, pi 2py. While writing the energies of various molecular orbitals, first write bonding orbital, next write anti-bonding orbital. Okay. Next write same orbitals with star mark, that is anti-bonding orbitals. Pi star 2px, pi star 2py, last orbital is sigma star 2pz. Here I am using O2 molecule. For example, here I am using O2 molecule. In O2 molecule, how many electrons are there? 16 electrons. These 16 electrons are arranged into above molecular orbitals. Up to here 8 and pz orbital 2, 10. In degenerate orbitals, filling electrons 11th and 12th electron. These two are degenerate. That's why each orbital filled with one electron only after pairing takes place. 13th and 14th electrons pair up with the 11th and 12th electrons. Here also same. 15th electron, 16th electron, no electron in last orbital, no electron, empty. It is the configuration of O2. The above one is the configuration of N2. 14 electron means N2 molecule. Up to 14, same order is followed. Above 14, that is from 15 onwards, we will follow this order. What is the major difference in the above two orders? Up to 8 electrons, no variation in energies of molecular orbitals. From 9th electron onwards, there is a slight variation. If atomic number is less than or equal to 7, then 9th electron enter into pi molecular orbital. Okay, in case of lighter elements. Whereas in case of heavier elements like like O2, F2, mixing of s and p orbitals not possible. That's why 9th electron enter into sigma orbital. 9th electron enter into sigma orbital. While writing the configurations of N2 and O2, you must remember the entry of 9th electron. In case of N2, 9th electron enter into pi molecular orbital. In case of O2, 9th electron enter into sigma molecular orbital. Okay, it is important point to write the configurations of both N2 and O2. I will explain shortcut also. Without writing the configuration, we will find bond order. But it is the regular way to find the bond order, writing configuration and finding the electrons in bonding and anti-bonding orbitals. Okay. After writing the configuration of N2 and O2, write the formula useful to know the bond order. What is bond order? Bond order is nothing but number of bonds between two bonded atoms. If single bond is present, bond order is 1. If double bond is present between two atoms, bond order is 2. If triple bond is present between two atoms, bond order is 3. Okay. Here the formula is bond order is nothing but number of bonds between two bonded atoms. Between two bonded atoms. The formula used to find bond order is bond order is equal to NB minus NA by 2. Here NB means number of electrons in bonding molecular orbitals. number of electrons in bonding molecular orbitals. That means orbitals without star mark. Simply Na means number of electrons in anti-bonding molecular orbitals. Number of electrons in anti-bonding molecular orbitals. Okay. After finding bond order, if bond order is 1, single bond is present between two atoms, 2, double bond is present, 3, triple bond is present. Okay. Bond order is directly proportional to number of bonds. Number of bonds increases, bond order also increases. If number of bonds increases, bond energy increases. If bond energy increases, bond length decreases and stability increases. Bond length decreases. These all are interrelated relations. First find bond order. After finding bond order, if bond order increases, what happens? Bond energy increases. Bond energy is directly proportional to stability. So, bond order increases, stability also increases. If bond order increases, bond length decreases. Bond order and bond length are inversely proportional to each other. Okay? It is very important for objective point of view how to find bond order, how many bonding electrons are there in given configuration, how many anti-bonding electrons are there. Now I am going to calculate bond orders for N2 molecule and O2 molecule. First example 1, N2 molecule. In N2 molecule, total number of electrons equal to 14 because atomic number 7, 7 plus 7, 14 electrons. If you observe the electronic configuration of N2 molecule, out of 14 electrons, number of electrons present in bonding orbitals, Nb value 10, Na value 4. Electrons present in anti-bonding orbitals 4. So, bond order is Nb minus Na by 2. That means 10 minus 4 by 2, 6 by 2, 3. If bond order 3 means triple bond is present between two nitrogens. Triple bond is present between two nitrogens. In N2 molecule, triple bond is present between two nitrogens. Okay? After finding bond order, if you observe the electronic configuration of N2, in N2 configuration, no unpaired electron. That's why N2 molecule is said to be diamagnetic in nature. In given electronic configuration, if unpaired electrons are present, it is paramagnetic, attracted towards magnetic field if unpaired electrons are present. In N2 configuration, no unpaired electron, that's why N2 is diamagnetic. N2 molecule is diamagnetic. Along with bond order, Magnetic behavior also predicted by using the electronic configuration. N2 is diamagnetic because in N2 configuration unpaired electrons equal to 0. By applying same formula, find bond order for O2 molecule and also magnetic behavior, bond order and magnetic behavior. O2 molecule. Atomic number of oxygen 8. In O2 molecule, 16 electrons are present. Z value 8. Total number of electrons equal to 16. If you observe the configuration of 16 electrons, electrons in bonding orbitals Nb equal to 10, electrons in anti-bonding orbitals equal to 6. Find bond order by using the above electrons. Bond order is equal to 10 minus 6 by 2, 4 by 2, 2. That means double bond is present between two oxygens in O2 molecule. In O2 molecule, double bond is present between two oxygens. Double bond is present. What about magnetic behavior of O2? If you observe the configuration of O2, O2 molecule has two unpaired electrons in anti-bonding orbitals. So, O2 is paramagnetic. O2 is paramagnetic because it has two unpaired electrons. Two unpaired electrons in anti-bonding pi molecular orbitals. O2 has two unpaired electrons in anti-bonding pi molecular orbitals. Okay, these are most important. N2 and O2 molecule. How to write the configuration in N2 molecule and O2 molecule? What is the difference between the configurations of N2 and O2? You must remember that point, that is while entering 9th electron in N2 molecule, 9th electron enter into pi molecular orbital, whereas in O2 molecule 9th electron enter into sigma molecular orbital. Because in heavier elements like O2 and F2, there is no mixing of 2s and 2p orbitals. That's why 9th electron enter into sigma orbital. If z-axis is considered as internuclear axis, pz form sigma orbitals, px and py form pi bonds. That's why they form pi molecular orbitals. That is also one of the important point to write the configuration. Okay. Now I am going to discuss about how to find bond order without writing configuration. That is shortcut, important. It is useful from 8th electron to 20th electron. If the molecular ion contain 8 electrons, minimum from maximum 20 electrons. Okay. You already know about the bond order of N2 molecule. N2 molecule has how many electrons? 14. For 14 electrons, bond order is 3. You already know. Based on the configuration. Okay. From 14 electron onwards, for every increase or decrease of 1 electron, bond order always decreases by 0.5 units. From 14 electrons onwards, for every increase or decrease of 1 electron, bond order always decreases by 0.5 units. Based on that point, write the bond order for remaining 15 electrons. Bond order decreases by 0.5 units. So bond order is 2.5. For increase of 1 electron, bond order decreases by 0.5. 2.0 is nothing but 2. 1.5, 1 or 1.0, 0.5 and 0. For 20 electrons, bond order is 0. Molecule with 20 electrons never exist. If bond order 0 means that molecule does not exist. Similarly, right left hand side also. For 13 electrons, bond order is 2.5, 12 electrons 2, 11 electrons 1.5, 10 electrons 1, 9 electrons 0.5, 8 electrons 0. The molecule with 8 electrons does not exist. It is the shortcut, very important for objective, to solve the objective questions without writing the configuration. Without writing N2 and O2 configuration, we will identify the bond order easily. Okay. I am giving some examples. For example, when N2 molecule is converted into nitrogen molecule is converted into N2 plus ion, then what about bond order? Nn bond order. Either increase or decrease, fine. Similarly, Nn bond length. Nn bond length. To solve this type of questions, use the tabular form, use the shortcut how to find the bond order. Okay. Here you already know about N2 has how many electrons? N2 converted into N2 plus after losing 1 electron. Okay. In N2, 14 electrons. In N2 plus after losing electrons becomes 13. For 14 electrons, bond order is 3. Bond order is 3. For 13 electrons, bond order is 2.5. So, what about bond order? Increase or decrease? Bond order decreases. Bond order decreases. So, right here, Nn bond order decreases. What about bond length? Bond length is inversely proportional to bond order. Apply this one. If bond order decreases, bond length increases. Bond length increases. Okay, I hope you all are understanding well. By using this shortcut table, you got clear idea about bond order. Bond orders are easily found for diatomic molecules or ions without using the configuration. One more model related to bond orders. Which of the following molecule does not exist? Here the options are given like this: He2 molecule, second one Be2 molecule, third one Ne2 molecule, fourth one all. If bond order becomes 0, then the molecule does not exist. You know already. Find the bond order for helium molecule. Helium, how many electrons are there? 4 electrons. In helium, 4 electrons are there. In beryllium, 8 electrons. Neon, 20 electrons. For 4 electrons, how to find bond order? If electrons number below 7, write the configuration and find bond order. For 4 electrons, configuration is like this: sigma 1s2 star sigma 1s2. So bond order is equal to bonding electrons 2 minus anti-bonding electrons 2, 2 by 2 by 2, 0. For this bond order 0. You already know about for 8 electrons bond order 0, or otherwise writing the configuration you will get 0. For 20 electrons also bond order 0. If bond order is 0, the molecule never exists. So the above molecules, above diatomic molecules does not exist. For isoelectronic species means having same number of electrons, their bond order also same. For example, in isoelectronic species, bond order remains same. Give an example. N2 molecule is isoelectronic with carbon monoxide, N2N CO. If you observe the number of electrons, here in N2 14 electrons, carbon monoxide also 14 electrons. So they have same bond order 3 and 3. Similarly, Cn minus and NO plus, same bond order. Cn minus has how many electrons? Carbon 6, nitrogen 7 after gaining 1, 14 electrons. NO plus also 15 minus 1, 14 electrons. Their bond order remains same. If isoelectronic species are given, their bond orders remain same. Okay, write this one. Important model. Among O2 molecule, O2 plus ion, O2 minus ion, O2 power 2 minus. Among these, write the order of bond order. First find bond order and write the bond order, either increasing or decreasing. While finding bond order, first observe the number of electrons present in given molecule or ion. So, I am writing number of electrons. In O2, O2 plus, O2 minus and O2 2 minus. Here number of electrons in O2 are 16, O2 plus. After removing one electron, 15, O2 minus. After gaining one electron, 17 and 18. First write electrons, next write bond order. So bond order is for 16 electrons bond order is 2. For 15 electrons bond order is 2.5. For 17 electrons bond order is 1.5. For 18 electrons bond order is 1. Among them, which one has highest bond order? O2 plus has highest. So, the correct order is O2 plus greater than, O2 greater than, O2 minus greater than, O2 2 minus. It is the decreasing order. It is the decreasing order of bond order. What about bond length? Bond length is related to bond order. Okay. Bond length is inversely proportional to bond order. By applying this, here O2 2 minus has lowest bond order, that's why it has more bond length, right? Reverse order. O2 2 minus greater than, O2 minus greater than, O2 greater than, O2 plus. It is also one of the important model related to bond order and also bond length. Okay. Okay, students. Thank you one and all. We will meet later. Thank you.